There is a theory that explains every particle, every force, and every interaction in the known universe. Scientists have tested it over 50 years, and it has never been wrong. Until now. In the last 3 months, CERN has found 2 new particles nobody knew existed and detected an anomaly so statistically extreme that 2 independent experiments are now quietly agreeing something is out there that our best theory of reality cannot explain. Okay, let's dive right into this. Welcome to today's Explainer, where we're looking at shattering the standard model with CERN's 2026 discoveries and the penguin anomaly. You know, for half a century, the standard model of particle physics has basically been the undisputed king of science. It's the rulebook for literally everything around us. But recently, the armor on that framework is really starting to crack. The stakes here are absolutely colossal, world-altering even. We might actually be witnessing the dawn of a totally new era of physics. So first up, 2 unprecedented discoveries from the LHC's 2026 run. Before we go breaking the fundamental rules of the universe, we kind of have to appreciate how incredibly well the model still works when we push it to its absolute limits. Let's take a look at the incredible new pieces of reality we just found. Check out this number, 84. Back in May 2026, the Atlas collaboration at CERN dropped a stunning announcement. They observed an excited composite particle called the BC star plus meson. Now, why on earth does that matter to us? Because it officially marks the 84th new hadron discovered at the Large Hadron Collider. Think about that. That is 84 brand new, never-before-seen particles that we've essentially just pulled out of the quantum static. Moving right along to the quark family tree and building a heavier proton, this brings us to the other massive recent discovery from March 2026. This one came from the LHCb experiment, and it's a particle known as the ZCC+. To put it in plain English, scientists basically built a new, ultra-heavy cousin of the standard proton. And finding this is absolutely crucial because it helps us fundamentally understand how quarks, the actual building blocks of matter, bind together. And this brilliant comparison illustrates exactly what they did. Over on the left, you've got your standard, run-of-the-mill proton. It's made of 2 light up quarks and 1 down quark. Pretty standard stuff. But on the right, look at the CC+ particle. By swapping out those 2 light up quarks for 2 much heavier charm quarks, scientists have observed an entirely different beast of a particle. Because of those 2 heavy charm quarks, this new particle is roughly 4 times heavier than a standard proton. 4 times. Honestly, it's literally like finding a massive boulder sitting in a pile of tiny pebbles. But here's the catch. You won't just see this boulder lying around. The Schick Plus has an incredibly fleeting life. It exists for just 45 femtoseconds. That is 45 millionths of a billionth of a second before it decays into 3 lighter particles. The standard model mathematically predicted this would happen, right? But it actually took the heavily upgraded LHCb detector snapping photos 40 million times a second to finally catch it with an undeniable 7 sigma level of certainty. It's just an incredible triumph for our current theory. Okay, but now we get to the penguin anomaly where the rules break. The shift here is profound, guys. You see, the standard model got that heavy proton perfectly right, but right next door, literally in the same particle collider, scientists are seeing something that the standard model gets entirely wrong. We are pivoting to an anomaly that is threatening this entire 50-year-old framework. Enter the so-called penguin decay. This is a really rare quantum process where a quark changes flavor and momentarily produces these ghostly virtual particles that emit other particle pairs before vanishing. And quick side note, it actually earned its quirky name back in 1977 because physicist John Ellis lost a game of darts to a student. His penalty? He had to use the word penguin in his next academic paper. He realized the Feynman diagrams for this process actually sort of looked like a penguin, and well, the name stuck. But don't let the name fool you. The physics happening here is absolutely no joke. Let's walk through the steps of this decay together. First, a bottom quark decays into a strange quark. During this process, it emits a lepton-antilepton pair. Now, the standard model has a very strict rule called lepton universality. It absolutely demands that this process should produce an equal number of different types of leptons, like electrons and muons. But step 4, that's the detonation moment. CERN has detected an imbalance. They are not equal at all. Which brings us to cracking the standard model, the 3.7 sigma threat. This imbalance is literally tearing at the seams of modern physics. And what makes it a genuine crisis is the sheer statistical weight of this specific, stubborn anomaly. Usually, weird bumps in the data just kind of fade away as you run the experiment more times. But this one, it flatly refuses to fade away. It is currently sitting at a 3.7 sigma significance. Now, in particle physics, a 5 sigma is required for an official, undeniable discovery. But let me tell you, a 3.7 sigma is a massive, flashing red warning light on the dashboard of our understanding of reality. So the crucial point here is understanding what that number actually means in the real world. A 3.7 sigma deviation, it's like flipping a completely fair coin 100 times and getting 69 heads. It's staggering. There was only a 1 in 16,000 chance that this anomaly is just a random statistical coincidence. It is highly, highly probable that the standard model is actually failing us here. Which brings us to the ultimate question, doesn't it? What exactly is causing the penguin anomaly? If the standard model says this imbalance shouldn't happen, what on earth is tipping the scales? Well, physicists are realizing that an unknown, ghostly participant, a particle not accounted for in any of our textbooks, must be briefly popping into existence during this decay and interfering with the results. So physicists are scrambling to rewrite the rules, and they've lined up a few prime theoretical suspects. We're going to look at them impartially here, as the scientific community is heavily debating all of them right now. First up is the hypothetical Z-prime boson, which would be a completely new force-carrying particle. Second is the theoretical leptoquark, this bizarre hybrid particle. And third, we have undiscovered particles from a framework called supersymmetry. Listen, finding any of these would radically expand our understanding of what the universe is actually made of. All right, let's look at the next frontier, searching for new physics. To see how this builds into our broader strategy, we have to recognize that the Large Hadron Collider has brought us to the very brink of this new physics, but finding the exact culprit, that might require some unprecedented new tools. We are shifting from the current LHC's limits to a massive, global effort to definitively crack this model open. If we trace the timeline, the stakes become crystal clear. Back in 2012, we found the Higgs boson, effectively completing the standard model. By 2015, the first stubborn signs of the penguin anomaly started appearing. Now here we are in 2026, and we have the 84th particle and heavy proton discoveries, showing our detectors are more precise than ever, while the anomaly just keeps growing stronger. This is all leading us straight toward a looming decision in 2028 regarding brand new infrastructure. To hunt down these missing particles and find out exactly what is messing with our penguin decays, CERN is proposing the Future Circular Collider. Just look at this comparison for a second. The current LHC is an absolute engineering marvel. It has a 27-kilometer circumference with 13 tera-electron volts of collision energy. But the Future Circular Collider, it would be a monstrous 91 kilometers around, delivering a mind-bending 100 TeV of collision energy. I mean, it would make the current LHC look like a high school science experiment. And honestly, we need that kind of power because, in all humility, there is just so much we still don't know. The standard model is a masterpiece, for sure, but it is vastly incomplete. Despite its 50-year reign, it can't explain dark matter, which makes up most of the universe. It doesn't include gravity. It can't explain why there is more matter than antimatter. The model is beautifully precise, but it is fundamentally missing the biggest pieces of the cosmic puzzle. And that makes the penguin anomaly a thrilling beacon, pointing us right into the unknown. Which leaves us staring at the edge of the map. With 84 new particles discovered, heavy protons behaving perfectly, but fundamental rules of lepton decay completely unraveling, we are forced to ask, if the standard model is fundamentally broken, what is the true fabric of our reality? What phantom particles are swimming right through us at this very second? It's a mystery that will absolutely define the next century of science. Thank you for joining me on this explainer, and keep your eyes on the data.